Good day, everyone. Thanks for joining in this for this webinar. The webinar's title is the Methanol Pathway to Hydrogen. We've got a long list of speakers for you today, but we hope we'll be sharing a lot of very interesting ideas about how methanol and hydrogen are really very synergistic products. My name is Tim Chan. I'm from the Methanol Institute. I'll be your moderator for today. So a couple of things that I would like to remind the audience for today before we kick off today's agenda would be, firstly, you're on mute. So if you look at your control panel on GoToWebinar, there is a tab called Questions. If you click on it, it's a drop-down menu, really. So like you can actually type in your questions in there and they'll be directed to the speakers during the Q&A sessions before we wrap up today's agenda. Another tab that you'd see on GoToWebinar would be a tab called Handouts. And we've got two handouts for participants today. The first of which is E1's white paper. This event is a collaboration between the Methanol Institute and E1. And E1 is also launching its white paper titled The Renewable Methanol Pathway to Green Hydrogen. And that will be also some of the materials that we use for a discussion that we will have later on in today's webinar. So do go on to the handouts tab, click on it. There are two handouts for you. Do download it before you log out from today's webinar, and you'd be able to get a copy of those two documents that I'm talking about. So just to quickly start and give an introduction, as mentioned, I'm from the Methanol Institute. We were founded in 1989 in Washington, D.C. More than 30 years later, we have 5 offices around the world. We are in DC, Brussels, Delhi, Singapore, and Beijing, China. So MI is the Global Trade Association for the methanol industry. And these are some of our members. We have a tiered membership system going from the biggest producers, methanol producers around the world, trickling down to smaller producers. Then you have your methanol distributors, methanol technology providers, and etc. Really, so it's really a huge group of different companies, but all coming together because of one common interest, and that is methanol. A quick introduction to how we divide the work in the Methanol Institute. We have a committee structure. We do have 4 different committees within MI. There is the Marine Fuels Committee, the Market Development Committee, the Product Stewardship Committee, and the Global Fuel Blending Committee. So each committee addresses a different set of issues. Methanol as a marine fuel is addressed in the Marine Fuels Committee. The Market Development Committee addresses a couple of different burgeoning applications of methanol as an energy product, as a fuel. The Product Stewardship Committee focuses on the use and safe handling of methanol. And the last committee, the Global Fuel Blending Committee, basically uses, or at least they focus on the use of methanol as a fuel for road transport. So that's my short introduction. We do have a long agenda ahead of us, so I'll not take up too much more time. These are our contact details. As mentioned earlier, we are in 5 offices around the world, so do feel free to reach out to us if you have any methanol-related queries. So for today's agenda, the first speaker on today's agenda is Greg Dolan. Greg Dolan is the CEO of the Methanol Institute. And Greg, I'll be passing controls to you, and you can start your presentation.
Great, thanks, Tim. And I also want to thank Dave Edlund for inspiring today's webinar with his excellent white paper on the methanol pathway to hydrogen. For those of you who have participated in some of our past webinars, you would have heard us refer to methanol as a future-proof fuel. And to me, there are really 2 sides to this phrase. First, as I'll go into in a little bit of detail, methanol can be produced from a wide range of conventional and renewable feedstocks. And then second, as a fuel, methanol can be used in combustion engines, but methanol is also an ideal hydrogen carrier for fuel cell technology applications. As a liquid at ambient temperature and pressure with the highest hydrogen to carbon ratio of any liquid fuel, methanol makes fuel cells practical for powering cars, trucks, ships, and even cell phone towers. Okay. Looks like I'm not, there we go. Okay, great. Globally, most methanol is produced from the steam reformation of natural gas. Mature technologies, plants have produced 5,000 metric tons of methanol per day. In China, they produce much of their methanol from coal gasification. But methanol can also be made from a wide range of renewable feedstocks. As a chemical derivative, methanol is an essential building block for hundreds of products that touch our daily lives. Paints, plastics, solvents, resins, car parts, building materials all begin with methanol. Methanol is also an emerging energy resource, a direct fuel, also a derivative for products like MTBE and biodiesel. And as we'll discuss today, methanol is an outstanding hydrogen carrier for fuel cell technology applications. Now, last year, methanol demand hit nearly 100 million metric tons. That's about 33 billion US gallons, or 125 billion liters. Of that methanol demand, about 2/3 is for chemical applications, and 1/3 of the demand is in energy. Over the last 10 years, we've seen methanol demand more than double. And that growth has been led by two markets: the direct use of methanol as a fuel, and also the production of olefins from methanol. Much of this growth has been led by China, which is the world's largest methanol producer and consumer. Recently, we released a joint report with the International Renewable Energy Agency, IRENA, Innovation Outlook Renewable Methanol. This was the first comprehensive look at renewable methanol. And when we talk about renewable methanol, we can put that into two different boxes. First is biomethanol, or methanol produced from biogas or biomass gasification. And then the second would be e-methanol, which is methanol produced from green hydrogen and CO2. Now, IRENA predicted that by 2050, global methanol demand could increase fivefold to 500 million metric tons. And of that 500 million metric tons, 115 million metric tons would be conventional natural gas-based product, 135 would be biomethanol, and 250 million metric tons would be e-methanol, again, according to the IRENA estimate. Now, when we talk about the transport sector, energy density matters. While methanol has roughly half the energy content of diesel or gasoline fuels, methanol has a much higher energy density than other alternative fuels that are being discussed today, including ammonia, hydrogen, and batteries. Now, we all like to color code our fuels. For methanol, looking at the bottom, coal-based methanol or coal gasification of methanol would be considered brown methanol, and that's primarily done in China. Gray methanol is produced from natural gas. Again, mature technology, 5,000 metric ton per day facilities. Now, that existing methanol plant from natural gas can also be turned to producing blue methanol, and that can be done by introducing hydrogen, green hydrogen as a feedstock, renewable electricity, or captured CO2 to produce blue methanol, where you've lowered the carbon footprint of an existing natural gas-based facility. For green methanol, again, we have two different pathways: biomethanol produced from biogas or biomass gasification, and then e-methanol produced from green hydrogen, renewable electricity, and CO2. Now, that CO2 can come from several different sources. It can come from industrial flue gases, unavoidable CO2 emissions from things like steel or cement plant. Methanol can also be produced from the CO2 can also come from biomass gasification, so a hybrid configuration where you get the hydrogen through electrolysis of water using renewable power, solar or wind power, and then the carbon part of the methanol molecule, CH3OH, can come from biomass gasification. Or in the future, as we see the technology for direct air capture of CO2 come online, we can produce e-methanol from hydrogen and direct air capture CO2. Now, the report from IRENA that we did also has very intricate assessments of the cost of production of biomethanol and e-methanol. On this chart, the gray bars across the bottom show you the price point for conventional natural gas-based methanol. The green portion of the bars are biomethanol. As you can see, depending on the biomass feedstock or biogas feedstock, some biomethanol is cost competitive with conventional methanol today. And what we expect to see as these technologies hit greater maturity, their costs come down even further. Now, the blue bars show you e-methanol. With a dark blue, conventional would be e-methanol using CO2 from flue gas, industrial flue gas sources, and the light blue portion of the bars coming from direct air capture. Now, here we expect that as we get to 2050, e-methanol will become price competitive with conventional methanol as, again, we achieve economies of scale. Today, the electrolyzers that are used to produce green hydrogen for e-methanol are built in the megawatts of capacity. What we'd expect to see over time as the cost for those electrolyzers will come down as we start going from producing megawatts to gigawatts electrolyzers. Now, the report with ARENA also includes a number of tables that show current biomethanol and e-methanol plants, as well as announced facilities. What I've done here is total all those plants up, so you can see where we expect the production of methanol from biomass and e-methanol to go in the 2022 to 2024 timeframe. And then the green portion of the bar, again, is all the other projects that have been announced to date, but don't have specific timelines. So we do expect to see much more methanol coming online from biomass, biogas, and e-methanol facilities. Really, the challenge over the next decade will be to ramp up this production to greater commercial volumes. Now, I'm also often asked, what is blue methanol or low carbon methanol? Again, that's taking existing natural gas-based facilities and reducing their carbon footprint, either with the addition of CO2 that can come from a neighboring industrial facility or from recycled CO2 within a methanol plant, or the addition of green hydrogen or renewable electricity. These are the tools to producing blue methanol by reducing the carbon footprint of an existing facility. Now, another way of reducing the carbon intensity of methanol from natural gas is to replace the conventional natural gas with biomethane or biogas. Now, companies like BASF and OCI BioMCN are doing this today with ISCC certified biomethanol produced on a biomass basis using biogas as a feedstock instead of conventional natural gas. The most recent e-methanol plant to opened last October in China. This is a liquid sunshine project, as they call it in China. It's using 10 megawatts of solar power to produce 2,000 metric tons per year of e-methanol. And I can tell you that in China, they are very keenly interested in the production of renewable methanol, and we expect to see that grow considerably in the coming years. Now, with that, I've just included here again the contact details for our global team. I'd encourage you to check out our website at methanol.org and also follow us on social media. We post news stories daily about the production of methanol as well as the emerging markets for methanol. And with that, I turn it back to Tim and look forward to the discussion. Thank you.
Thanks, Greg. So we do have some interesting information that you shared down there. One thing I would like to remind the audience is that the information that was shared in Greg's presentation came from the ARENA report, and that's available online for download also if you've not downloaded it already. So next up, we have Dave Edlund. Dave Edlund is the CEO and founder of E1. He's also one of the co-authors of the white paper that we've been speaking about today. Dave, I'll turn it to you right now.
Great, thank you very much, Tim, and thanks to all my panelists, colleagues for being here to help out with this webinar. So what I want to talk about now is more on the technology side, following up with that detailed introduction to methanol, and especially renewable methanol that Greg shared with us. I want to talk about how we go from methanol to hydrogen, and that's very important as we look at an electrified future, both from the stationary perspective and mobility perspective. There we go. To begin with, let's talk about the chemistry that's happening here. So methanol, it's the simplest of alcohols, one carbon alcohol, and it reacts readily with water to generate hydrogen and carbon dioxide. Now, the energy that is applied to make this reaction occur at reasonable rates is thermal energy. It's not electrical energy, and that's a very important distinction when we look at other renewable pathways to hydrogen. Ideally, we would get only hydrogen and carbon dioxide from this reaction. In practice, we also get some carbon monoxide, CO. Because of that, it's necessary to purify the product hydrogen if that hydrogen is going to be used in a low temperature fuel cell, like a proton exchange membrane fuel cell. Now, if the hydrogen is going to be used in a combustion device, probably little concern about the CO that's present. CO also is a fuel. Or if the hydrogen is going to be used for industrial purposes, there may be little need to remove the CO, or maybe CO can be partially removed. But for purposes of low temperature fuel cell applications, we definitely have to pay attention to that carbon monoxide contamination. And that's built into the hydrogen generator product line that I'm going to show you in the subsequent slides. Most often, we hear about water electrolysis as the pathway to renewable hydrogen. And it's a very mature technology. It's been deployed in large scale pretty much around the world. And it works. There's nothing wrong with it, except for the fact that it uses a large amount of electricity. And to be more specific, we need 50 to 55 kilowatt hours of electricity to generate 1 kilogram of hydrogen by electrolysis of water. To say that another way, if we have 1 megawatt of electricity applied to an electrolyzer over an hour, you get 20 kilograms of hydrogen. In comparison, that really isn't a lot. Now, if we instead consider methanol reforming, we need very little electricity. We just need electricity to run the machine, and that is less than 0.04 kilowatt hours of electricity per kilogram of hydrogen. Again, the energy to react methanol with water is thermal energy. Thermal energy is much cheaper than electricity. In fact, electricity is the most expensive form of energy that we have available to us. And if we do look at the thermal energy that's used to reform methanol with water, again, it's a modest amount. It's 7.5 kilowatt hours of thermal energy to generate 1 kilogram of hydrogen. We can achieve very high energy efficiency of the mid 80% based on lower heating value, converting methanol to hydrogen and purifying that hydrogen to fuel cell quality specs. So we have at Element 1 3 different product lines of hydrogen generators, and they're shown in these 3 photographs. All of these hydrogen generators are fully automated for unattended operation. On the left is our S series. It's a small stationary hydrogen generator. It's been deployed delivering up to 0.7 kilograms of hydrogen an hour. So that mates well with up to a 10 kilowatt fuel cell. And it's ideal for backup power and small primary power applications, again, mostly stationary. In the middle and on the right, we have representations of larger hydrogen generators. These go up to just shy of 10 kilograms of hydrogen an hour. The center figure is what we call our M series. That's designed specifically for heavy-duty mobility applications. It's designed to be put on a vehicle. And on the right, we have very similar configuration, a somewhat different controller, which is designed for large stationary applications, again, primary and backup power. Now, to integrate a hydrogen generator with what I'm going to generically call a hydrogen consuming device, the schematic for that, or the integration process, is actually very simple. And to be clear, a hydrogen consuming device might be a compressor if we're talking about hydrogen fueling stations. It might be a fuel cell if we're talking about electric power generation, or it could be some other device or process, industrial process that consumes hydrogen. The interface is a low pressure buffer tank, and that's shown by the green block in the middle of each of these two figures. On the left, we have a very simplified schematic for a hydrogen fueling station, and on the right, a fuel cell power system. The hydrogen generator produces hydrogen, which flows directly to the buffer tank. This is purified hydrogen. Typically, it's going to be 99.99% purity with less than 0.02 ppm. That low pressure buffer tank then feeds the hydrogen consuming device. And if it's a compressor, the hydrogen then is drawn into the compressor where it is discharged at very high pressure to a storage tank for further dispensing into vehicles. The pressure in that high pressure storage tank provides feedback control to the compressor. The hydrogen generator is simply looking at the pressure in that low pressure buffer tank. The buffer tank will cycle between a minimum pressure and an upper pressure or a high pressure. And all the hydrogen generator is trying to do is maintain pressure within that range. Now, the same is true if we're looking at a fuel cell, which is the configuration shown on the right. The fuel cell is going to draw pressure from that low pressure buffer tank and make electricity. The electrical output from the fuel cell is most often put onto a common bus with a battery bank, and from that bus, the load is then supplied. It can be a very dynamic load because the battery is very good at responding to instantaneous power demand as well as peak power. The fuel cell simply needs to see pressure in the buffer tank, and again, the hydrogen generator is simply working to keep that buffer tank between a minimum and a maximum pressure range. The fuel cell control is driven by the state of charge of the battery bank. So the state of charge would be maintained between a minimum and an upper set point, and the fuel cell simply works to keep that battery bank charged. Now, when we think about onboard hydrogen generation, we have a very interesting comparison to make with storage of compressed hydrogen on the vehicle. And to illustrate this, I'll consider a North American heavy-duty truck. And in this figure, behind the cab, we have this black enclosure, which contains multiple carbon fiber cylinders for storing high pressure hydrogen. This configuration is designed to store about 80 kilograms of hydrogen. Now, 80 kilograms of hydrogen in a heavy duty vehicle like this will give a range of up to 600 miles. And we can also generate that amount of hydrogen over the same number of hours that it would take to drive that distance with a relatively small sized hydrogen generator producing only about 7 to 10 kilograms an hour of hydrogen. To drive 600 miles, we need a little over 1,000 liters of methanol water mix. It's easy to put more tankage on this vehicle, so you could easily extend that range by a factor of 2. Tim, I seem to be stuck. If you can advance me to the next slide. There we go, thank you. So when we think about the various factors that are important to operating a vehicle, an electrified fuel cell vehicle, and compare onboard compressed hydrogen with onboard hydrogen generation, we find that the hydrogen generator is better in terms of lower capital cost, smaller size, and again in this photograph, the green outline on that black box shows the relative dimensions of the hydrogen generator. It takes half the space that would be occupied by the cylinders for compressed hydrogen. The cost of hydrogen, if we make it from methanol, is going to be in the $3.5 to $5 per kilogram range versus probably $10 to $16 a kilogram if the vehicle is being refueled with compressed hydrogen. And as I mentioned before, we can double the range easily by putting liquid methanol water on the vehicle and making hydrogen on demand versus storing compressed hydrogen. Now, the hydrogen generator, again, regardless of whether it's a stationary or mobile application, will have 3 normal operating states, and that's on, where we're making hydrogen, off, where it's not energized, it's not electrified, and then what we call a hot standby condition. Hot standby is a normal operating state whereby the hydrogen generator is at its operating temperature and is maintained at that operating temperature by a very modest amount of electric power, perhaps from the onboard battery bank or perhaps by a plug-in umbilical. And transitioning from hot standby to on making hydrogen is very fast, on the order of 1 to 2 minutes. Typically, whether we're looking at stationary or mobility applications, the fuel cell would be sized for the average load demand of that application, with peaking power and instantaneous power provided by a hybridized battery bank. Tim, if you could move me to the next slide. Thank you. Now, there are a number of applications, commercial opportunities that we're looking at. Top of the list is hydrogen fueling stations. And again, because we can make hydrogen at an advantageous cost from methanol versus transporting compressed hydrogen to a fueling station, this is a very attractive opportunity. Hydrogen generation onboard heavy-duty vehicles, including trucks, trains, and most recently ships and boats, is also very attractive. And in these two figures, in these two photographs, we have a medium-duty truck made by FAW. This truck has a fuel cell power system and an onboard hydrogen generator. The hydrogen generator is circled in green and it's positioned behind the cab. Same real estate that would have been used for cylinders for compressed hydrogen. Last fall, we completed 5,000 kilometers of on-road testing in China without a single fault or failure on the part of the hydrogen generator. Now, I mentioned ships and boats. The maritime sector is of a very high degree of interest, and we're embarking on a new joint venture with 2 partners, maritime partners out of New Orleans, Louisiana, and Ardmore Shipping out of Cork, Ireland. And I'm going to leave it to my colleague Stuart to talk a little more about that. But we see auxiliary power and for inland waterways, even propulsion power, as being very attractive in the maritime space. And then, of course, distributed power, whether that be backup or microgrids for stationary power generation. These are all very attractive opportunities where we can compete cost effectively. And if we build on renewable methanol, we can have a very green footprint as well. And I think that brings me to the last slide, if you'd advance me, Tim. Correct. Thank you very much. I'll turn it back to Tim. Thank you.
Thanks, Dave. Dave, I just want to hold you for 1 sec here, because I got a pretty interesting question. Usually we'll leave it to Q&A, but I think this can really bring some perspective as to what you're talking about. And the question was, how much energy as percentage of the hydrogen that's being compressed or stored is required to compress hydrogen to, say, for example, 700 bar?
I'm going to work from memory, which is always a little bit risky, but I think that the answer to that is about 15%.
So that would be a 15% loss of the hydrogen that you're trying to store?
That's correct. That's correct. Yeah. And so I'm just going to expound on that for a few seconds here. Obviously, if we're not storing compressed hydrogen and alternatively, we're making hydrogen and delivering it at low pressure to a fuel cell or to some other industrial process, we're saving energy. That's a more efficient loop to follow.
Okay, thanks, Dave. So next up, we have Robert Meaney. Robert Meaney is the Director of Engineering and Technology from Weber Research and Advisory. Robert, let me pass you controls right now.
All right, thank you, Tim. Just make sure that the mouse is working. All right, thanks, Tim. So just a brief overview for those that may not have heard of Weber Research is what we do is we help connect investors and strategic partners with technologies and capital projects. And we do this in three main ways. We have independent research, which we provide on a subscription basis that covers a lot of capital projects, market research, and the renewable energy transition. We also provide technical consulting around investment due diligence and capital projects through independent engineering. And then our advisory firm, Armistead Street Partners, helps connect those looking for that finance to end users that are looking to invest in the renewable energy transition or in capital projects. All right, it's working for me, Tim, by the way. So like a lot of people, we started out about 2 years ago really looking at the renewable energy transition. And what we kept running into is we attended all these great seminars on explaining the difference between gray, blue, and green hydrogen. But it really never progressed for us in a lot of the seminars we attended past that. So our thesis, and when we built our hydrogen roadmap, was really to expound upon the idea of getting, how do you get hydrogen from renewable energy dense areas, Middle East, Australia, Arizona, to end users that are lacking renewable energy. And so we focused on what we call the hydrogen midstream sector, being ammonia, methanol, compressed hydrogen, and cryogenic hydrogen as the four main sectors that everybody's looking at. And what we found through this was basically that the big missing piece that for methanol and ammonia, when we originally looked at it, was the conversion back to hydrogen, which Dave just explained with E1, how that's possible for methanol in both small and large applications and even on vehicle applications. And I would just like to thank Methanol Institute, as I would have never actually met Dave and understood this if it hadn't been for y'all's free seminars that you guys put on. So thank you guys and your members for putting this on and making it open to the public. So I appreciate that. So like a good ex-capital project person, we focus a lot on safety. And when I talk safety, I really wanted to bring in an expert to help us understand this better for future fuels. So I've worked with Baker Risk in the past, and what they do is they specialize in site studies for insurance companies and post-incident analysis around a lot of these future fuels. If there is an incident, they're typically the ones that get called to come analyze and say what went wrong and how it went wrong and how to mitigate that issue in the future. So they provided a little bit of insight to us around just the flammability and explosive radius potential of future fuels and how to mitigate that. And methanol being a liquid similar to diesel, gasoline, ethanol, and having those similar characteristics kind of provided somewhat of a less dangerous public safety exposure when compared to other gaseous fuels that are in much larger quantities. So by minimizing these quantities in public spaces, we minimize hence the risk. That's why methanol has been able to provide that kind of consistent approach to fuels. We also looked at the logistics, it's a hard word, logistics of these fuels. And when I originally did my hydrogen roadmap, I actually stopped, like a lot of people, at just the hydrogen content of the fuels, meaning methanol's hydrogen content, ammonia's hydrogen content. Ammonia has more hydrogen than methanol. So ammonia transports more hydrogen than methanol. Well, if you look at the entire value chain and the steam methanol reforming process on the back end, you're actually adding 30 to 40% green hydrogen on the back end of your green methanol transportation cycle. So the benefit of E1 system is you're actually transporting, if you use pure methanol from like Australia to Japan, Australia to Korea, you're actually transporting more hydrogen to the end user. And this is something that's kind of missed unless you're looking at the entire value chain. Then as far as logistics, we're also considering the storage cost per kilogram of hydrogen. And so methanol as an atmospheric liquid requires less storage cost compared to ammonia that may be using LPG type cylinders or cryogenic hydrogen or compressed hydrogen. And that dollar per kilogram has to be recouped at the pump, at the end user, in some certain circumstance. So that buildup cost and that total CapEx cost is important to remember when looking at that total value chain. Now, I know I'm speaking to the Methanol Institute crowd, and I'm not trying to pile on ammonia here, but this is a specific case looking at ammonia at gas stations versus methanol at gas stations. And when we look at this, we have to look at kind of where the majority of the cost is associated at the pump. A lot of the marketing we hear is $1.50 per kilogram of hydrogen, $2, $3 per kilogram of hydrogen. That does not take into account the full buildup cost that we see at the pump, $16, $14, $15 per kilogram. And so this midstream sector is so important in reducing the cost of hydrogen to end users. And when we talk ammonia and the higher cracking temperature necessary there and the toxicity exposure to the public, the current approach is to have a centralized cracking process, compress that hydrogen, store it high pressure, and then transport that to the gas station. This limits your efficiency and increases your cost at the end of the day, whereas a system like Dave's can take methanol all the way to the gas station. And I'm sure Greg will recognize these numbers, but there have already been gas stations converted to methanol using existing 10,000 gallon tanks. And this can be done for $20,000 to $75,000 per gas station 10,000 gallon tank. And just as a comp, a 10,000 gallon tank using an E1 system would produce essentially 5,000 kilograms of hydrogen on site. Oh, let me go back one. All right. So when we talk safety and the mitigations there, we talk logistics, storage, and distribution. All this leads to a buildup cost of hydrogen at the pump. Now, what I'm showing here is bare cost, meaning no profit margin added in yet. And this can change based on location, production type, owner type, etc. But what I want to talk about is just these individual bars and what they mean. When we talk CapEx, that is your one-time cost to invest in a facility, a $100 million facility, and you're recouping that cost over X many number of years. That is applied to how many kilograms of hydrogen you produce. Same with the OpEx cost, meaning your feedstock, your personnel, your maintenance and consumables. All that builds up into your OpEx cost. And then your transportation, that's your hydrogen storage. How long are you transporting? How much are you transporting it? Are you going to be able to feed one hub or multiple hubs with the hydrogen that you're transporting? So and how long are you taking to fill up your tank or disperse your tank? Currently, compressed hydrogen takes about 10 to 12 hours to load into a truck. So that is a person's time that is sitting there at the pump, waiting for it to load or waiting off to the side at a hotel somewhere for it to load. Methanol can do this very efficiently. It offers that back-end steam methanol reforming that reduces the cost and offers this cut cost of $6, $8 per kilogram of hydrogen. Now, E1 Marine was clever, and they found out, well, why do I want, like Dave said, why would I want to pay a gas station for this necessarily? Why don't I just do it on board the ship and generate power there? Then you don't require the purple cost. Now you're reducing your cost of hydrogen even further. So that's the benefit of the mobile application to the E1 system. And what did this cost really result in at the end of the day? If we apply this, I'm going to apply it to 3 different sectors and show kind of some differences. So this is Toyota Mirai's $15,000 hydrogen fuel incentive. you essentially get 40% more range using green methanol, which is essentially green hydrogen after it's converted to hydrogen. And then you decrease emissions, you decrease costs to the end user. All right, so I'm going to give ammonia a second to shine. And when we're big LNG guys as well, so we talk a lot about LNG in the future that we see there. And so large scale power generation, turbine systems, when we talk multi-100 megawatt systems and what's being talked about in Japan and Korea, this is where blue ammonia has an opportunity, is displacing the LNG market with close to carbon neutral fuel application. Biomethanol to hydrogen here offers a close second. It just really depends on the efficiency of the turbine systems when they become commercialized and where a hydrogen turbine ends out versus an ammonia turbine. But where we really see the benefit of methanol is going to be in the mid to low scale power generation. And so this, and the way to read this is y-axis is fuel consumed, x-axis is dollar per megawatt. So when you're looking at biomethanol converted to hydrogen using a high efficiency fuel cell, like a low temperature PEM fuel cell, give Ballard a plug, a Ballard fuel cell on the back end, it beats the efficiency of other applications, the conversion, the cost. It makes a lot of sense for stationary power, on-ship power, and vehicle power. And that's it for me.
Thank you, Robert. We do have some questions for you, but I think let's leave it to the end because we're a little behind time. So I'd like to move on to our next speaker for today. And our next speaker is Nicolas Pocard. He's the Vice President for Marketing at Ballard Power Systems. So Nicolas, I'll pass controls to you right now. Okay, there you go.
Thank you. Thank you very much. Very happy to be with you today. So I'm going to talk about the application. You know, what are we going to do when we have hydrogen generated from methanol and how it can be used, and where are we today in the use of hydrogen and fuel cell technology for heavy duty mobility. Trying to get control of the slides. Okay, so I've been deploying and developing fuel cell technology for more than 40 years now. This is what we do as a company. I don't seem to be able to move my slide, so I need your help to move to the next slide because it's not moving.
I'll do. Sure. Let's do that.
Okay, so as I said, we are mainly focusing on the heavy duty side and really looking at regions where there is decarbonization policies and towards green mobility, and we are really today active in North America, in China, and in Europe. That's where we are mainly active. Next slide. And so where we look today, where hydrogen makes sense, and it's back to the energy density. You know, if you're looking at, using, compared to batteries, hydrogen provide a unique, very high energy density. But as energy density comes, it's energy density per weight, which is great, but volume is an issue. And the application where you're looking today, heavy mobility, coach and buses and trucks and train and ships, need a lot of hydrogen because they're going to need a lot of energy to move those vehicles, and then the storage is really an issue. And I think Dave highlighted earlier some of the challenges if you have to store a lot of hydrogen, compress it on board on a vehicle. And the bigger the application is, like a marine vessel, then the bigger the challenge becomes. And therefore, we need to look at all the options which are available in order to store this, hydrogen or hydrogen precursor or carrier into an application. And especially when you have a lot of, need for hydrogen to be used by the fuel cell. Therefore, looking at methanol is a really attractive option in order to increase the storage capacity for the application. So why fuel cell makes sense for the application? If you go to the next slide, you will see that, and we start to see more and more application using it. It's a very strong, value proposition. I come to that in later. We're looking today at applications starting with your centralized depot refueling, so fleet-based vehicle, bus, transit bus, truck fleet, rail yards, or ferries on the marine side coming back to a location so we can control the supply of hydrogen. And really looking at application which will be the harder to abate, like heavy duty mobility, where plugging a locomotive or plugging a marine vessel might not be the best option. So looking at an alternative way to decarbonizing those heavy duty applications. Next slide. And hydrogen really, and a fuel cell actually inside compared to batteries, enables you to avoid any compromise on the payload, on the range. So you can have very long, 600 miles, 1,000 miles vehicle operation without having to compromise on the weight. And if you want to do that with batteries, you're going to have to pack a lot of batteries on board of your vehicle, on a truck, for example, and then the trucks start to be now carrying more batteries than it can carry actual goods. So it's very important to be able to maximize the range, maximize the payload for the operator, as well as because those vehicles, electric vehicles are more expensive than diesel vehicles, you want really to also optimize the usage of your vehicle. So you want to have a maximize utilization of those vehicles. So you don't want those vehicles to be plugged in on a charger for hours. You want to be able to use them on multiple shifts. And that's why having a very quick refueling time, by refueling methanol or hydrogen in those, very quick, so you don't immobilize the vehicle. So that's very important for commercial application. So you want to maximum range, no compromise on payload, and to be able to utilize the vehicle as much as you can. So fuel cell technology coupled with hydrogen or hydrogen carrier like methanol enables you to really basically have the same mobility operation that you have with diesel today. Next slide. So, just quickly, as I mentioned, Ballard is what we are doing. We have now people dedicated to development of fuel cell technology and mainly focusing on heavy duty mobility. As you can see, buses, truck, train, ships, we're putting them on the water, on the tracks, on the road. And that's what we do. We have a tremendous expertise. We have over 88 million kilometers of vehicle operation on the road, and we're gathering data every day. So we really understand how fuel cell operates and what it needs, and really we bring that expertise to the mobility market. And I want to share with you some of the application today where fuel cell makes sense and where there's a need of a lot of energy and where methanol can provide a carrier to a hydrogen feed. Next slide. So the products we're doing at Ballard, we have, I don't want to go into detail, but we have a range of a fuel cell engine, if you want, in order to meet all the application from a bus to, from forklift to a bus to a truck to a locomotive. So ranging from 30 kilowatt, I would say, to 200 kilowatt building blocks, but fuel cell can be put in parallel. So you can imagine, for example, we're doing some projects where we can put, several 5, 6, 7, 200 kilowatt building blocks together to do over a megawatt of power system for a locomotive or ship. Next slide. And the same thing on stationary side. So we can also look at fuel cell for backup power on small telecom sites. But also we can look at very large megawatt backup power system for data centers, for example. And it can be in building blocks. So we have 2 series of building block at Ballard. We have a 200 kilowatt cabinet, or we're also developing a containerized 1.5 megawatt solution. And then you can have several of them together for larger power generation systems. Next slide. So if you look now at the mobility a little bit more, and want to show you some example of actually vehicles on the road. So if you go to the next slide. So today, fuel cell buses have been deployed across cities in North America. That's an example of the buses we're doing with New Flyer, So buses, there's over 50 of such buses in California alone in operation, and the numbers is growing. So you have some in OCT, OSC Transit, or Sunline. So fuel cell electric buses are now being deployed as an alternative or complement to battery electric buses because they provide longer range, they can go on a highway, higher speed, and they are much less impacted by tough winters or hot summers. So it provides the operator really very stable operation, long range, regardless of the temperature outside. So next slide, going to be a bit so an example of a truck here is a Class 8 truck, which is in operation in a port of LA, a drayage application with a fuel cell. You've been replacing the diesel engine for zero emission drayage truck. Next slide. And you have also smaller trucks. We have a fleet, actually, that's an example of a fleet of 500 of those trucks. I think it's a 6 to 8 ton trucks, which is operating in the southern part of China and then in Shanghai. And actually, overall, there's 3,000 of those trucks in China operating on multiple shifts. So, you know, from very early days to late in the night to deliver goods in the Chinese city with no emission and no noise. Next slide. An example also of a similar truck, but for UPS in California. Here we have a range extender here. We're building a number of those vehicles been deployed for operation around Ontario, California. Next slide. And as another truck we're doing in Canada. So just show you really, and it's back to the example that Dave showed you earlier. So this truck is 60-ton truck, is going to need a lot of hydrogen. So looking at, you know, what was the best option to store energy on board of the vehicle. And, you know, methanol is an attractive offer for the very high power density in terms of volume compared to hydrogen gas. Next slide. And as we move up, you know, those very big trucks, then, you know, here is an example of a trucks we are doing for a platinum mine, actually in South Africa with Anglo American. And there's going to be around 800 megawatt of fuel cell system installed. As you can imagine, it's going to use a lot of hydrogen. And so I think some, you know, looking at options, is the hydrogen gas really the best option for those vehicles? And I think that's what we're exploring now, just to look at how do we address the super heavy mobility where you need a lot of energy to move those vehicles. Next slide. I want to go a bit faster to those applications. You know, example of a tram line where, you know, in operation in China, using also a fuel cell tram. Next slide. Good example of a passenger train we have in Europe on the next slide, developing with Siemens, so regional train operating, and then same thing in UK, all of them using fuel cell for zero emission train operating on non-electrified truck. And the next slide. To finish up a bit faster, yeah, this is a problem we do with a CP rail locomotive in Canada. Same thing, a lot of energy is going to be needed for this. And the last slide I have on my presentation, next slide, is a marine project. So it's an example of a ferry, but same challenge here. Are we going to store all the energy you need on board of a marine vessel? You know, when, you know, so methanol is actually very actively being thought as a solution for to couple with fuel cell for zero emission marine. So just wanted to show you some application where we believe that a high power density of methanol coupled with the you know, zero emission of fuel cell can really provide a solution. So that's the end of my presentation, I believe. And yes.
Thank you, Nicolas. Yep, I think that's the end of it. We'll leave some of the questions that we have for you to the Q&A session, but I think we will have quite a bit to discuss during the panel discussion after this. So next up, I would like to introduce our next speaker. Our next speaker is Stuart Crawford. Stuart Crawford is the Managing Director of E1 Marine, as Dave had mentioned earlier. So I'll quickly pass controls to you right now, Stuart.
Yes, thanks, Tim. So E1 Marine, as Dave indicated earlier on, is it's a joint venture company where Could you move on to the next slide, please, Tim? Thank you. So it's a joint venture company between Ardmore Shipping and Maritime Partners and Element 1. And this is intended to drive the uptake of the methanol reformation technology in the maritime industry. One of the reasons that it's critical is the maritime industry has been challenged by the IMO to reduce its carbon intensity. And if you could jump to the next slide quickly, please, Tim. So what does carbon intensity mean? It's carbon dioxide produced per ton mile on the vessel. So referencing back to 2008, the IMO requirements are that we reduce that carbon intensity by 40% by 2030 and by 70% by 2050. So what we need to do is find more effective ways as an industry of reducing our carbon footprint. Now we can achieve some of that through larger vessels, reducing the specific fuel oil consumption on vessels, and we can use better hull forms, etc. But that will only ever get us part of the way towards achieving these milestones. What we need to do is find a way to actually reduce our carbon footprint further. And methanol offers that solution. So methanol is an ideal fuel to carry hydrogen. And if we can produce hydrogen on board, and we can produce enough hydrogen on board to displace generators or engines on smaller vessels, etc., so we suddenly are able to achieve these targets. Could you jump to the next slide, please, Tim? So we see in the marine industry, we believe, certainly here at E1 Marine, that hydrogen is the solution. Now, as Dave Edlund had referred or indicated earlier, it's not just methanol that's producing the hydrogen in the methanol reformer, it's water as well. So we have a 62.5% water combined with 67.5%, 62.5% methanol, 37.5% water, and that increases the hydrogen yield by 33% on board. That hydrogen is very clean, it can be used in fuel cells, and the carbon reduction by using the methanol, you actually reduce your carbon dioxide emissions by up to 35%. The combined effectiveness of the methanol and the fuel cell is close to 50% thermal efficiency, which compared to a normal internal combustion engine at around about 35%, shows you that we can use this energy and we can use it very, very effectively. And it's when we combine all of this together that we start to see our carbon footprint reducing significantly. When we use biomethanol or green methanol, we see our carbon footprint drop to zero. That's critical. That's what's going to get us to the future. We've talked a little bit about the technology and how the technology works. What we've got now is we've got a small video that I would like to share with you, which shows you the practical application of that conversion of methanol and water to hydrogen. Tim, could you run that video, please?
Methanol mixed with water in a 1:1 molar ratio is an ideal liquid carrier for hydrogen. 1/3 of the product hydrogen comes from water. This water needs to be desalinated and deionized. It may be drawn and purified from the water the vessel sails in. The methanol water mixture flows through a heat exchanger into a catalytic reactor, wherein the methanol plus water is cleanly converted into hydrogen mixed with carbon oxides and other gases, without the release of SOx, NOx, and particulate matter. This gas mixture then flows through a novel purifier that delivers high purity hydrogen as the product stream and a waste stream, or fuel gas as a byproduct. This fuel gas is used to heat the process. The product hydrogen may be consumed directly by a fuel cell to generate electricity, or direct into an internal combustion engine, supplementing the normal liquid fuel regenerating water as a byproduct. In the future, we will have the option of capturing carbon dioxide from the fuel gas stream, potentially driving the overall carbon intensity to very low values, in certain cases, even negative values.
Presentation. So one of the beautiful impacts of this is that water can come from the water that the vessels are sailing in. Obviously, it needs to be desalinated, it needs to be purified, it needs to be deionized, but we're getting 33% of the hydrogen from the water we're sailing in. And that means that we don't need to transport that water directly to the vessel. We can just pull it from the environment that the vessel's sailing in, which is ideal. And what that means is methanol is that key carrier for hydrogen. That's what we believe at E1 Marine. We believe that coupling up with the methanol reformer will provide that solution. And yeah, this is how we see the future developing. I think that's it for me, Tim. Thank you.
Thank you, Stuart. The last speaker that we have for today is Christian Somborn. Christian Somborn is Director of Business Development at Proman. Christian, just give me 1 sec and I'll give you controls right now. There you go.
Thank you, Tim. My name is Christian Somborn, as Tim said. I'm with Proman. Just as some little key facts and figures about the Proman family of companies. We're headquartered in Ballard, Switzerland, that's near Zurich. Over 30 years of experience, 34 years in Trinidad and Tobago was our start. Now we have production facilities both in Trinidad and Tobago, Oman, and the United States. Over 1,600 employees operating in 4 continents across the globe with engineering offices in Europe as well. Yeah, over 10 million tons of installed capacity, EPC experience, as well as 13 time chartered vessels. Needless to say, we're big believers in the methanol economy. Just looking at just our global footprint and where we're placed to meet the future demands of hydrogen as a renewable energy source and methanol as a hydrogen carrier. As I said before, our production facilities diversified throughout North America, also Oman. And looking at the world in the future, we're also seeing a lot of growth opportunities throughout North America, Latin America, Northern Africa, Europe, as well as Asia and Australia. Moving on. You know, we are the second largest merchant methanol producer in the globe, but we don't stop there. We're also really committed to this green transition and have over the last year announced either some major investments or major developments in this field. You'll see that we announced our participation in a project in Quebec, in the province of Quebec in Canada, called the Varennes Carbon Recycling Project. This is a 100,000 ton per year biomethanol facility, which is going to be utilizing an 87.5 megawatt electrolyzer for makeup hydrogen. We use waste, so municipal solid waste, gasify it and convert it to methanol. The idea there is, in the beginning, is to actually use that biomethanol for the European automotive pool as a blend fuel. However, we see a lot of this application actually going in the future more into the marine sector. As well, I think another big landmark investment for promoting methanol as a clean and low carbon fuel was with Stena Bulk. This is a joint venture in which Proman and Proman Shipping and Stena Bulk have committed to transitioning into methanol dual-fired reciprocating engines. So I think Robert made a really good presentation in which he highlighted you have both the methanol as a hydrogen carrier in fuel cells, as well as in reciprocating engines. And I think that's something we cannot dismiss, even though I do applaud E1 and their joint venture partners at Ardmore, to what they're doing with onboard methanol reformation. I think I'll skip this slide. I think we've heard a lot about why methanol from all the other announcers. Also, Greg did a great job talking about the various pathways to creating methanol. So, using both MI's and IRENA's methodology, both from biomass, renewable electricity, natural gas, and coal. Those are the different colors of the rainbow, so to speak. I think that's very much understood by this team here. So why Proman decided to use methanol-powered ships? I mean, aside from being a global leader in methanol production, I think we just had to show the commitment that we see this as a future-proof fuel. So as the world transitions from fossil-derived methanol to more sustainable pathways, we felt that this was just the ideal fuel to actually send our chemical tankers around the globe with. So again, then the transition to actually finding sustainable ways of production was actually key to our strategy. So, we're not only looking at low carbon methanol, meaning blue methanol from Trinidad and our United States operations through, carbon capture in the flue gas stack, but we're also looking at further developments into green methanol projects and constructing those projects. So as I said before, we've already announced that first project in Canada. We're actively part of a consortium, the North Sea project in Belgium, and we also have further developments ongoing globally. And one of the biggest considerations of why we decided to go with methanol, because we're also among one of the top 10 nitrogen-based fertilizer producers, also in ammonia, was basically mostly safety. And this is something Robert did a great job highlighting in his presentation. Anything can be more ambient temperature, and you don't have a possibility of having a huge, I would say, safety issue with leaks that present with ammonia, for example. You could literally poison everybody on board of a ship. We just felt that this, from a safety and operational standpoint, and also the OEM readiness to start implementing methanol engines, as well as, the track record that we've seen with people like Ballard, as well as all the other work from all the big fuel cell manufacturers, we felt this was just the right way to go. All right, Tim, I think I need your help. Presentation seems to be stuck. Also, a major consideration of why methanol is because we currently have a lot of bunkering possibilities with the current chemical distribution network that we have. So as well as the safety and the way of handling, and our view that reducing the spill implications, we also felt that due to the current global network that methanol actually enjoys, it'd be very easy then to make the step change into having it as a bunkering fuel, which we felt was very important in securing, getting the support from all the different ports and local authorities in implementing methanol as a marine fuel in grand scale. Next slide, please.
Okay.
I won't spend too much time with this, but I'm happy to have this conversation with everybody, both on the panel as well as anybody listening, with regards to how we see the general pricing economic considerations today for marine applications specifically. But we do believe there is a significant case today already to use methanol in existing fleets, and you can actually retrofit this quite easily in reciprocating engine applications, and we look forward to new ship builds with fuel cells as well, because we also think there's very compelling economic cases there. All right, I think that is it from my end, Tim. Again,
Thanks,
thank you,
Christian.
everyone. I tried to run through this because I know we're a little bit over time.
Thank you so much. Yes, we are indeed slightly behind time. So I'm going to be mindful of the time. We do have a panel discussion as well as a Q&A. But firstly, I would like to thank all presenters for their presentations. There was some very useful information in there. I think we have a lot to discuss about. Initially, I thought that maybe I wanted to kick off today's panel discussion by going through some of the key takeaways from the white paper that E1 wrote. But I think we did receive a question which might be actually a bit more interesting to discuss and kick off today's discussion. So what I'm going to do, presenters, is that I'll direct the questions at you. But if you do have any kind of inputs, do feel free to chime in and provide your insights on the issue that we're speaking about. So one of the first few questions that we've got in today's webinar, and actually we got quite a few of this. So I'll start off with Dave. And the question really is, you need green hydrogen to produce green methanol. Why produce green methanol, then convert it back into green hydrogen when you can use green methanol straight as an energy product, say, for example, in ICEs or even in fuel cells?
Right. Good question. But it is not correct that we must have green hydrogen to make green methanol. That represents one pathway of many. As Greg and Christian pointed out, there are other pathways to get to green methanol based on renewable methane, renewable CO2 mixtures, and those do not require green hydrogen. Direct air capture of carbon dioxide or using carbon dioxide from industrial byproduct streams, of course, does require green hydrogen. And why do that? Well, here's the reason. If you are going to transport hydrogen made from electrolysis of water using wind or solar, how far are you going to transport it? And if the answer is more than a few hundred kilometers, then you are paying a lot just to transport the hydrogen. Plus, you have the carbon footprint inherent in transporting that hydrogen. One can invoke pipelines for hydrogen, but the reality is that they are rare. There are very few. Building extensive pipelines is a generational event that takes trillions of dollars. It's just not a near-term solution. Once you've made methanol, you have a liquid under normal conditions, and that is very easily transported at a very low cost and very low carbon footprint. So that's really the two reasons to look at green methanol as opposed to focusing only on green hydrogen.
Dave,
anybody else? Sure.
Yeah, what I would like to pick up on there as well is if we use methanol direct into an internal combustion engine, as was being suggested, then we still see the CO2 emissions, we still see NOx emissions, etc., associated with the high pressure, high temperature methodology of internal combustion engines. But when we use the methanol mixed with water in a methanol reformer and fuel cell setup, what we actually see is a better thermal efficiency. We see efficiencies approaching 48 to 50% by using a combination setup versus that internal combustion engine efficiency of maybe only 35 to 38% efficiency. So we do see additional gains using methanol to hydrogen conversion on board, certainly on board vessels anyway.
Thank you, Stuart. So one of the things that we discussed a lot about today was, really methanol is a very good carrier hydrogen, and I believe most of our speakers would believe in that. But then the focus really is the end product, right? It's hydrogen that we're delivering to, for example, a fuel cell, or it could be that ICE. Anybody can chime in on this question because I'm just throwing it out there. What are your thoughts on the staying power of methanol as a hydrogen carrier? Because we always talk about the future being operated on a hydrogen economy, for example. Would methanol still play a part? Is this a transitory fuel, or is there going to be some staying power in the future where you'd have maybe a methanol economy supporting a hydrogen economy?
Tim, maybe I'll start on that. One of the benefits of using methanol, it is a simple molecule, CH3OH, that has a lot of different feedstocks. Now, molecule itself doesn't really care if it was made from gray natural gas or blue methanol or renewable green methanol. It's the same molecule. So methanol really facilitates the transition over time in the bluing and greening of our transportation fuels.
Yeah, I'll add in there that I do believe that methanol is one of nature's gift in the energy sector. You know, hydrogen is the best feedstock for making electricity in a fuel cell. And so I think hydrogen is going to be firmly rooted in a green energy future. But how do you handle that hydrogen? It's not easily handled. You can compress it and store it at very high pressure with associated costs, both capital cost and operating cost, and associated safety concerns. I think the most logical, sustainable future is where hydrogen is made at the point of use as it's needed. And you could do that with water, with some hydrogen storage, or you can do it from methanol and water. And if you take that pathway, now you truly are freed of the intermittency of renewable electricity. And so I don't think it's a transitionary fuel at all. I think it's the solution that will define our clean energy future.
Hey, Tim, can I jump in on this real quick?
Sure.
So just thinking future-proof fuels, what we've done on our side is we've looked at kind of the dynamics of current fuels applying atmospheric carbon capture to reduce their carbon intensity versus the de-escalating cost of renewable methanol over the next 25 years. And so the capital build out, recoup costs, same buildup type costs that we did for hydrogen, we applied that to current fuel slates and measured their efficiency versus what an E1 system could do. And this is just for that stationary bunkering, and people laugh at me when I say this, the hotel load power for ships. And the biomethanol at $800 per metric ton is more efficient, more cost effective than the long-term price of LNG with 100% direct air capture. Now, that obviously can scale over time as the direct air capture gets more efficient and more cost competitive, but methanol's pricing is also going to come down over time. So this is a very long-term carbon neutral or carbon negative solution. And Greg, you got to add a gold methanol to your chart for carbon negative methanol, just so you can get that.
Thanks, Robert. So there was a question that I wanted to ask the panelists, and I think I'm looking at the questions that were also that the audience also had sent in, and I think I'm going to combine this one. And really is, what are the key challenges that you foresee in the adoption of methanol as a hydrogen carrier? But my question really was from a policy perspective also. So if you could give maybe like the first two thoughts of your mind as to what the key challenges might be, and also address the policy gaps that are in play today for the adoption of methanol as a hydrogen carrier, that would be great. So who wants to start on this one?
I'll jump in. You know, one of the issues that we see from a policy perspective is there's a tendency to pick winners and losers. You know, right now there's a big focus on battery electrics. So wanting to electrify particularly the light duty fleet, but also the heavy duty fleet, buses, trucks, and ships. And, you know, there's a real challenge there to try to get everything to run on batteries. When we look at methanol, it opens up a lot more opportunity. It produces it. When you're looking just at battery electrics, you're really putting all the burden on the vessel operator or the car builder. When you look at methanol, you bring in the entire value chain. So now you have the ability to produce low carbon and net carbon neutral fuels that can be used in these vehicles and vessels over time. And policy really needs to take advantage of that and look at these questions from a well to wheel or well to wake basis, rather than just trying to pick winners and losers and trying to say, well, we're going to electrify everything.
Thanks, Greg. Actually, just because you mentioned the idea of electrification, I wanted to ask the rest of the speakers and the panelists. And it seems like, I mean, at least from a government policy perspective, in some regions that we've observed, you know, electrification is like that cop out, right? It's that easy solution that you want to get to. I mean, it's just an easy term to throw out. I mean, there are also challenges with electrifying your transport fleet. And so I just wanted to know, does anybody have any ideas on that? How does fuel cells or even hydrogen generators play into this discussion that we're having right here?
I could take a shot at that if y'all are okay with it. So we just released our vehicle multi-factored rankings, looking at small vehicles, delivery vans, trucks, and semi-trucks. And battery electric's great, small applications like Greg said, but as it starts to scale up, you start running into limitations with C factors, with weight versus energy density. And these things don't translate as well as 100% solutions to larger applications. So for instance, where we see the kind of the ceiling for this for 100% battery electric is if you take the Class 8 truck, anything over 200 to 300 miles, you're going to need a hybrid approach. And that's kind of where we see that dynamic changing. And so something like an E1 system on board a semi-truck for long distance hauls or even short distance, depending on your location and geographics, makes sense. And anything above, trains, ships, etc.
Thanks,
and just expand a little bit on the impact to infrastructure, which is a big word now in the United States, at least. You know, it's easy to think about battery electric vehicles in the context of the vehicle alone, but mass adoption of battery electric vehicles is going to have a profound impact on the grid. And that is not to be understated. It is not a topic that gets a lot of consideration in most political arenas, certainly the political arena here in the United States, and it's seldom addressed in the news media. But it's not a simple step to take to go from vehicles which run on liquid fuels to vehicles which run on electrons only, driven by batteries. So the infrastructure is a huge piece of this, which warrants its own webinar. And that is where fuel cell electric vehicles, and they will be hybridized with batteries, but fuel cell electric vehicles, I think ultimately will win out in a certain sector of the market. Battery electrics are great in some areas, but it's not one solution fits all. And so I do see a huge opportunity for fuel cell electrics. And because methanol is a liquid fuel, I think it has enormous potential for filling that future need without having to invoke an infrastructure, which is very challenging to get to.
And continuing with this thought, Dave, you know, from Proman's perspective, we also view making renewable electricity and carbon capture into renewable methanol as a way to help balance the grid. So not only do you have to, you know, and also will help instigate further renewable electricity generation and being able to actually help with any type of curtailments that you see right now, because there's not enough backbone, long distance electrical infrastructure to actually dispatch that electricity when it's actually needed. So we think methanol, renewable methanol, is also a very elegant solution because you have it in liquid form. It can be used for ground transportation, marine, you know, all those applications, but also it could be used as a backup generation as well, and actually used to actually balance the grid out. So when we look at infrastructure as a whole, and you look at the whole value chain, yes, it has direct applications and use cases in mobility, but it can also help stabilize our grid as we know today. And I mean, Dave knows this better than anybody. You know, the United States grid is something, it's a patchwork of grids that was created over 100 years. It's going to be very hard to transform that over a decade and actually get the amount of renewable electricity out there that this current administration is seeing as its vision. So we do believe that renewable ammonia, renewable methanol are really the way forward to do that.
Thank you, Christian. So I wanted to go on to some of the questions that we had from the audience because I'm mindful of the time. And I think there were a couple of questions addressed to you, Christian, and I think I do also have my I do have my thoughts on that. But we just wanted to know basically from a producer standpoint, what are some of the top line ideas when it comes to the economics of producing renewable or biomethanol? I don't think we have to go into the details, but basically maybe you can give some high-level thoughts on what you think about that. That would be very helpful.
In terms of how we see the costs coming down over time, or are you more
the costs coming down over time?
Yeah, well, look, like anything else, we need some type of government incentives. I mean, you see it with, you know, I'm going to pick on EVs just to make the case. You know, EVs, even photovoltaics and wind, all had government policy that assisted them to actually generate the scale necessary for mass adoption. And I believe we're in a little bit of chicken or the egg situation where, yes, renewable hydrogen is getting a lot of press and you'll see a lot of hype around it, but renewable methanol is definitely not getting its fair share of the attention, and it's something that we should actually pivot to. Now, I know that we've done a great job as the Methanol Institute and all the other members, you know, to say that you can reform methanol into renewable hydrogen, right? But from a producer standpoint, we also have to make the case that you have ambient, you know, direct air capture. I mean, that is something that has a huge future and is a way to address increasing numbers of CO2 levels in the atmosphere and in the ocean water. You also have, you know, the case that we can take and decarbonize our existing gray black infrastructure by actually doing the flue gas stack carbon capture. And methanol coupled with renewable hydrogen is a way to do this. So from our standpoint, yes, as more renewable methanol projects come to market, which you know, Greg showed us that cumulative table of all the announcements that are being made, you're going to see cost savings over time on the main equipment. And to be clear, it's really the big drivers not only are electrical price, which luckily there's a lot of great announcements in the market, specifically in Northern Africa, Middle East, United States, South America, and also Australia, where you're getting to prices on a kilowatt hour basis that are almost like 1 cent, right? When you start getting electricity that's that cheap, all of a sudden electrolysis is really compelling. And what we really need to see is the scaling up of electrolysis equipment over time and the unit costs per megawatt installed coming down as well. So that's still going to take a few years to ramp up. You know, you have to build the whole industrial supply chain to do that. And factories need to build up that capacity. But what we really do need is more incentives from the government level and policymakers to actually see that future transpire. Now, on the other side, in terms of another pathway, more biomethanol pathway, I think there's a lot of incentive at the moment already, and that's why we actually are participating in this project in Quebec, the Proman Carbon Recycling Project. But, you know, waste and, you know, stopping the use of landfills, I think would be a huge policy change, and being able to make use of our waste that is only going to grow exponentially over time and produce chemicals like methanol. I think that's also a huge target market where that technology is going to come down. And you know, one of the biggest arguments that we face internally, where we have these world-class scale facilities, is aggregating enough inputs to actually have these economies of scale, like we're used to in the petrochemical sector. You know, using natural gas. You know, that's going to be decoupled. We're going to see a lot of smaller units across the globe spread out, and it's going to be more localized production for more localized consumption. So the only way to get the type of cost drivers to bring things to an acceptable level to the marketplace is innovation and cost savings over time. And again, we need policy to help facilitate that, because the early adopters are going to pay a premium. There's just no way, two ways about it.
Thanks, Christian. So I just want to pose you one more question before we go on to our next speaker, and I want to give them all a chance to answer some questions from the audience. So, I mean, if you had 2 points that you could make to answer this question, right, and the question would be, what can ports do in order to stimulate and or accommodate the offtake of methanol for the maritime sector? So just 2 points off the top of your mind, what would that be?
Sorry, can you repeat the question? I didn't catch the first part.
Sorry, the question is, what can ports do in order to stimulate and or accommodate the offtake of methanol as, I think it will be a bunker fuel here?
Participate in more pilot programs, but we're seeing a lot of that already, initiative taking place in Europe specifically. Port of Ghent, for example, where we're associated with the North Sea project, they're actively involved. Rotterdam as well, Antwerp, Amsterdam, they're all looking at bunkering methanol. You're seeing a lot of innovation. I mean, Methanex also just recently completed a bunkering program. I think North America is lacking that initiative, that drive, but I think that's a lot of it, again, going back to the whole policy discussion. Singapore, I would hope, is going to actually expedite their programs. I know that there's been a lot of interest in the past, but hopefully we'll see that catching some more traction. So yeah, it's more about public perception and maybe, and I'm going to pick on Greg here for a second, and you, Tim, Methanol Institute doing a little bit more work to educate the public outside of just MI's membership about the merits of methanol bunkering and methanol as a marine fuel.
And
Thanks,
just
Christian.
to pick up on that point, Christian, thank you. We did a report last year that found that there's methanol storage capacity at more than 100 ports around the world today. Typically 50,000 metric tons or more storage capacity, particularly at the 5 largest ports in the world. And the cost to get that methanol from the storage tank that's already in the port onto a vessel, to bunker it on a vessel, we're talking an addition of $8 to $10 per metric ton. So it's a very small cost to move that methanol within the port and get it onto a vessel going forward. And as Christian noted, 2 weeks ago, Methanex at the Port of Rotterdam did the first bunker barge to vessel transfer of methanol that involved the Port of Rotterdam, Vopak, and other partners.
Thanks, Greg. Okay, I want to move on next, but we're still staying on the same topic, which is the maritime sector and methanol as an energy product for the maritime sector. And the next question is to Stuart. Dave, if you have any thoughts, please do chime in. The question is, are you intending to capture the CO2 once the hydrogen is reformed on board a vessel?
Yes, so in regard to this, there is the ability to capture that CO2. That will come in the future. The methanol reformer itself produces a very high intensity stream of carbon dioxide. And the very fact that it is in excess of 50% carbon dioxide in the stream lends itself very, very well to carbon capture. I'll pass this on to Dave now, because I know it's something that Dave is looking at from a technological perspective. Dave?
Yeah, thank you, Stuart. You're right. We have a unique opportunity in the methanol to hydrogen generator for CO2 capture. Unlike conventional engine technology, we're not limited to only capturing CO2 in a low pressure exhaust stream. We have an internal process stream inside the hydrogen generator. At that particular location in the hydrogen generator, we have 85% of our total CO2 emissions as CO2 at pressure above 10 atmospheres. And that makes it very attractive. Stuart said also very high concentration, approaching 50%. That makes it very attractive for CO2 capture. And we've started the engineering studies on that this month, actually. So it is work in progress, and we think it has enormous potential in both maritime as well as stationary applications.
And I believe there was a follow-up question to that, is what do you intend to do with that carbon once it's captured? This is where it leads itself into that renewable sector. So that can then become the feedstock for renewable methanol in the future.
Thanks, Stuart. So one question I wanted to ask Dave, we still have you here, is have you guys done any life cycle analysis on carbon for methanol that's being used in E1 reformers? Dave, I think you might be on mute.
Sorry, I hit the wrong button. If the question is related to the life cycle analysis with respect to carbon emissions for the hydrogen generator, the answer is no, we have not done those studies. We do use pretty much conventional materials, primarily common steel alloys, and so they have very long lifetime and very easily recycled. But no, we have not addressed the detailed life cycle assessment, especially with respect to greenhouse emissions for the hydrogen generator itself.
Dave, I think maybe the question was more about emissions from using methanol as that hydrogen carrier in your reformers instead of the materials.
Okay, so if we're looking at well to wheels or well to wake emissions, yes, we have done some analysis on that. Actually, most of our work is just repeating what others have done there, especially the work out of Argonne National Labs. And as has been pointed out, what your net greenhouse gas emissions are depends strongly on what the source of methanol is. If the methanol is from a renewable resource, the carbon intensity is extremely low. It can be 1/10 of the carbon intensity of making hydrogen using grid electricity and electrolysis. If you use renewable methanol that has an even lower carbon intensity, you can find yourself in negative numbers relatively easily.
Thanks, Dave.
I think just to expand upon that ever so slightly, from an IMO perspective, where the IMO looks at things on a tank to wake basis rather than that well to wake basis, using methanol direct into an engine, your carbon emissions are very, very similar to a conventional liquid fuel. However, using that methanol water mix in a reformer and then utilizing it in a fuel cell, we do see reductions of up to 35% in carbon dioxide.
Thanks, Stuart. So I think we do have one last question that I want to throw out to our presenters, because we're slightly over time. And I think the question will be, we're always talking about range extenders in methanol slash fuel cell systems, or, well, okay, let me rephrase that. We're always talking about methanol fuel cell systems as range extenders in vehicles. This implies that you will also need expensive power batteries. Does it make sense from a total cost perspective? I'm going to give it to Robert first, because I think we've not heard from him for a while.
Oh, I'm good with that. If you guys don't want to talk to me, that's okay. We've looked at it just from when I think Dave showed the metric just about the comparison of pricing between the hydrogen gas cylinders and the methanol system. And as you scale up in size, I mean, right now 80 kilograms of storage is the equivalent price to an E1 reformer on board. You're using the same fuel cell system, the same battery system. So the further you scale up your hydrogen storage, the more economical the E1 system becomes. Even in Blue World and others that are doing similar aspects, it does make sense when compared to high pressure hydrogen. From a battery perspective, just depends on kind of a combination of things, your price of methanol, how you're reforming it, And then you have to compare basically your CapEx and your OpEx over like a 20-year period. We did a brief study just on autonomous vehicles in this as part of our vehicle study. And methanol scored very much in line with the small vehicle perspective with hydrogen.
Thank you. So with that, I'm going to wrap up today's Q&A. We're slightly over time, so I do apologize for that. Just a quick reminder before we end off today's session, do not forget to download your handouts. It's on your control panel. So there are 2 handouts there. First of which would be today's slide deck. Second of which would be the E1 white paper on the renewable methanol pathway to green hydrogen. So with that, I would like to thank all my speakers as well as attendees for taking the time to join us today. For the questions that we have not been able to answer, I'll circulate them around our speakers, and they'll be able to get in touch with you if we have not answered those questions. So with that, thank you, everybody.
Thank you.